This is the homework for page 452 for finding the area between two curves. Problem number 1, because we're doing 1, 3, and 5, the graph is already given for you, so you don't have to graph it yourself. They give you that f of x is equal to x squared minus 6x, and g of x is equal to 0. And again, they've already given you the graph, which looks something like this. This is in your book that you can take a look at. So there's your parabola, and so you can see from this graph that the top curve in this case is going to be the x-axis, and the bottom curve is the parabola itself. So when we find the area that's bound between the two curves, and so we're looking for this area right in here shaded in green. So the area between those two curves would be the integral. We need to find the point of intersection between the two curves, so we need to find this point right here and this point right here, which are really the x-intercepts. So we're going to set x squared minus 6x equal to 0, factor out the x, and we get x minus 6. So our zeros are x equal to 0 and x equal to 6. So we're going to find the area from 1 to 6. Now remember, it's the top curve minus the bottom curve, and in this case the top curve is the x-axis, which is 0. Don't really have to write that in my problem, but just for emphasis. And then we're going to subtract, and make sure you put parentheses because you got to distribute that negative to everything. The bottom curve is x squared minus 6x dx. So that's the same thing, of course, as the integral from 1 to 6 of negative x squared plus 6x dx. When I find the antiderivative of that, I will get negative x cubed over 3 plus 6x squared over 2, which is 3x squared. And we're going to evaluate that from 1 to 6. And at that point, that's an arithmetic problem. You can check that on your calculator or check the answer in the back of the book. But I'm not going to do the arithmetic in the interest of time. If you have questions on that or you're not sure where I got something from, you can come and see me and talk about that. All right, let's move on to problem number 3. In problem number 3, we have two parabolas. The first parabola is x squared minus 4x plus 3. And the second parabola is negative x squared plus 2x plus 3. Now I'm not going to sketch the graph because again that graph is in your textbook, but I do need to find the intersection of the two functions, so I'm going to set them equal to each other. X squared minus 4x plus 3 is equal to negative x squared plus 2x plus 3. The 3's are going to subtract out. I'm going to add x squared to both sides, and I'll get 2x squared. I'm going to subtract 2x from both sides and get negative 6x. Factor out the 2x, and I get x minus 3. So the points of intersection, x equal to 0, x equal to 3, and the graph in your book will confirm that. So now we're going to find the area from 0 to 3. Now remember, you have to look at the graph, or you have to find some way to determine which curve is on top. So let's take a minute and say I don't have a graph of this function, and for some reason I don't know how to graph, and I don't know which curve is on top. Well, we know that the area is bound between, if you think of a number line, all of the area that we're looking for is bound between 0 and 3. So whichever curve is on top over that entire interval, and whichever curve is on bottom, same thing, is on the bottom in that entire interval. So what I could do to determine which curve is on top, if I couldn't graph it, didn't have a graph, is choose a number inside the interval. For example, I'm going to choose the number 1. And I'm going to find f of 1, and I'm going to compare it to g of 1. And obviously, or hopefully it's obvious, whichever output is greater, that's the curve that's on top in that particular interval. So if I find f of 1, that would give me 1 minus 4 is negative 3, and negative 3 plus 3 is 0. If I find g of 1, I'll get 1 squared is 1. That'll give me negative 1. Negative 1 plus 2 is 1 plus 3 is 4. So now I know that the g function is on top. Now, it was likely that the g function was going to be on top because it's the parabola that opens down and the f function opens up. Lots of ways to think about this, but this is one strategy you can use if you have just two curves and you need to figure out which one is on top and which one is on bottom. All right, so let's go back to the problem. So I know that the g function is on top, so that's going to be the top curve, negative x squared plus 2x plus 3, minus the bottom curve, which is x squared minus 4x plus 3. Again, don't forget to put parentheses around the bottom curve. That's the integral of 0 to 3. When I combine like terms, I'll get negative 2x squared. 2x plus 4x is 6x, again, distributing the negative. 3 minus 3 would be 0 dx. I'm going to find the antiderivative of that, which will give me negative 2x cubed over 3 plus 6x squared over 2, which is 3x squared. And that's going to be evaluated from 0 to 3. When I substitute 3 cubed is 27. 27 divided by 3 is 9, times negative 2 is negative 18. 3 squared is 9, times 3 is 27. So that's the upper bound evaluated. Substituting in 0, I get 0. Negative 18 and 27 is 9. So the area between the two curves is 9. Problem number 5. In problem number 5, my two functions are f of x is equal to 3 times x cubed minus x, and the other curve is g of x. Again, the x-axis is bounding the region. I am going to show you this graph because it looks like this, and we did talk about this in class, if you recall, and in the interest of time, they already give me the intercepts. Yeah, I would just set this equal to 0 to find them, but in the graph I can see that. Remember, we're finding the area bound by the curve in the x-axis. And in region number 1, I'm going to call this region 1 and this region number 2. In region number 1, the cubic is on top and the x-axis is below. And in region number 2, the x-axis is on top and the cubic is below. So we're going to set up two integrals to represent all of the area that we need, the net area that we're going to collect here. So I'm going to collect area from negative 1 to 0. In region number 1, the cubic is on top. I'm going to go ahead and distribute that in. That would be 3x cubed minus 3x. The bottom curve is 0. Now I'm just putting that in for emphasis. You don't have to write minus 0. And then I'm going to add, so that integral would collect the area of region number 1. Now I'm going to collect the area of region number 2, which starts at 0, stops at 1. The top curve is 0. Now this is important because now you have to subtract. You have to put a negative in front of the parenthesis, 3x cubed minus 3x. Again, I just distribute. I could have pulled the 3 out. It doesn't really matter. dx. And that integral would represent the area of region number 2. And so now I'm going to work those independently. So when I find the antiderivative, all right, let's go to some of the ones now that have, that the graph was not given. Now number 17 is an interesting problem, and I definitely want to work that one. So I have y equal to 1/2 x cubed plus 2. The second curve is y equal to x plus 1. Now notice they're giving me several curves in this region. X equal to 0 and x equal to 2. All right, so we got to graph 4 curves. The graph is not given in this scenario. So let's take a look at the graph. So y number 1, or the cubic, 1/2 x cubed plus 2. So we have a vertical shift up 2 units. The 1/2 is going to slow the growth a little bit. I mean, we basically just need to see the behavior. Let me move that down a little bit. Sorry about that. All right, so let's move the x-axis down a little bit. So we're going to vertical shift up 2 units, and it's a cubic, a basic cubic with a coefficient of 1/2. Then I have y equal to x plus 1, so rise 1 and run 1, so we have a line. Okay, so that I graph the cubic, I graph the line. Now, x equal to 0 is a vertical line. I'm going to draw it in red. So x equal to 0 is this. And x equal to 2, 1, 2 is the vertical line like that. So what we're really finding here, hopefully you are able to figure this out, is that the region or the area that we're trying to collect is this region right in here. So we have to ignore all of the other stuff that's there. I have two vertical lines, a cubic. I have a line with a positive slope. But the region that I want to find the area of is the green region. So when I find that area, I can see from the vertical line that I'm going to start collecting the area at 0, and I'm going to stop collecting the area at 2. And in that region, the curve that's on top is the cubic, so I'll have 1/2 x cubed plus 2, that's the top curve, minus the line x plus 1 dx. And so when I find the antiderivative of that, I'll get, let's see, x to the 4th over 4 times 1/2 would be 1/8 plus 2x. You know what I should have done is combine like terms first. Let's back up and do that. It's early, so I'm not focused. 0 to 2, 1/2 x cubed minus x, and then I have a plus 2 and a minus 1, so I have a plus 1 dx. All right, now let's find the antiderivative. So that would give me, again, 1/8 x to the 4th minus x squared over 2 plus x. I would evaluate that from 0 to 2. So I'd substitute in the 2, substitute in the 0, which will give me 0. And again, you can do the calculations and substitute, and you can check your answer in the book. So that's how you do number 17. Okay, moving on to number 19. I have a parabola. In number 19, f of x is x squared minus 4x. And I have the x-axis. G of x is equal to 0. Now, in graphing this, if let's say you're on a quiz or a test and you don't remember how to graph this, you can't figure out how to find the vertex. Remember what we said is that you could, well, first of all, let's find the points of intersection. What are the x-intercepts of this parabola? So x squared minus 4x equal to 0. Factor out x and get x minus 4. So x is equal to 0, x is equal to 4. So again, like I said before, I know that all of the area is bound between 0 and 4. And because in this case I only have 2 curves instead of 3 or 4 like I had in the last one, it's very evident to me that the curve that's on top in this region stays on top the whole time. So I'm going to choose a number between 0 and 4, like I did before. For example, I'm going to choose 1. And I'm going to find f of 1. So f of 1 in this case is 1 squared is 1, minus 4 is negative 3, and f of 1 for the other function, 0, is 0. Whoops, that's g, sorry about that. So I can see that the g curve is on top, the x-axis is on top, and the parabola is below. Now, if I really want to graph this thing, I just want to remind you from Algebra 2, the quick way of finding the x-coordinate of the vertex is the x-coordinate of the vertex is x equal to negative b over 2a. It's really, if you think about it, it's the first or the front part of the quadratic formula. That gets you the x-coordinate of the vertex, and then the plus or minus square root of b squared minus 4ac over 2a, that moves you to the right, to the right side x-intercept, and then back to the left symmetrically from the vertex to the left-hand x-intercept. So just to show you, we could get the vertex and we could graph this. So in this case, b is 4, so the opposite of negative 4 is 4. A is 1, so the x-coordinate of the vertex is going to be 2. And then the y-coordinate is going to be f of 2, so 2 squared is 4, and 4 minus 8 is negative 4. Again, all I did was took the 2, substituted in to get the y-coordinate. So now I know that I have a parabola that's 2, 1, 2, 3, 4. Is that what we had? 4, yeah. It opens up like that. We also know the points of intersection, so I missed a little bit here, are 0 and 4. And the x-axis is clearly on top, okay? So we're going to collect the area from 0 to 4. Top curve is the x-axis, 0 minus bottom curve, x squared minus 4x dx. Find the antiderivative. We get negative x cubed over 3 plus 4x squared over 2, which is 2x squared. Evaluated from 4 to 0, I would substitute in the 4, and then I would substitute in the 0, which in this case will be 0. Do my calculations, and I would have the area that is enclosed right in here. Okay, number 21. 21 is a parabola and a line. So I have f of x equal to x squared plus 2x plus 1. I have g of x equal to 3x plus 3. Make sure I copied that right. Yep. All right, so again, the parabola, if you didn't know how to find the vertex or graph, or if you thought it was going to be too time-consuming or labor-intensive, you could use that strategy since you only have 2 curves. But I need to figure out where they intersect, so I'm going to set f of x equal to g of x. So I get x squared. Remember, you have to get this thing equal to 0, minus x to find the roots. Minus 2 equal to 0. So factor x, 2, 1. I want a negative in the middle, plus equals 0, x equal to 2, x equal to negative 1. So I know that I'm going from negative 1 to 2. So I'm going to choose 0 in between to evaluate f of 0. F of 0 gives me 1. G of 0 gives me 3. So I know that the g function is on top and the f function is on the bottom. So I'm going to set my integral. I'm going to collect area from negative 1 to 2. The top function, as we said, is the g function, or the linear function, 3x plus 3. The bottom function is the parabola, x squared plus 2x plus 1. A graph will confirm this. I'm going to combine like terms, negative 1 to 2. That would be negative x squared. 3x minus 2x is 1x. 3 minus 1 is 2. I'm going to find the antiderivative, negative x cubed over 3 plus x squared over 2 plus 2x evaluated from negative 1 to 2. Evaluate the function at 2, minus, sorry, let's erase that, it's a mess. Come on, eraser, there you go. Minus the function evaluated at 0, and of course that's 0 again, and you get your answer. Verify it in the back of the book. All right, let's see, we've got a couple more here. 23. 23 has 3 functions. Y equal x, that's the identity function. Y equal to 2 minus x is another line. And y equal to 0. So let's see what we got going on here. We can graph this one pretty easily. Y equal to x is 45-degree angle through the origin. Y equal to 2 minus x. Let's graph that one in a different color. So this one is red. This is blue. So y equal to 2 minus x, I have a y-intercept of 2, a slope of down 1, right 1. So it looks something like that. And now this is important. The y equal to 0, let's see, let's put that in green. Y equals 0 is the x-axis. So the region that we're trying, because you'll notice that there are 2 different regions of area enclosed here. The region that we're looking for is this region right here because it is enclosed by all 3 of the given functions. So the area that we're not looking for, we are not looking for that region. So be careful because there are 2 regions of enclosed area. I'm looking for the region that's enclosed by all 3 functions. So the first thing I can see from my graph is I need to figure out, I'm trying to click a color here, sorry. I need to figure out where the line y equal to x, which is right here, intersects the x-axis, which is obvious that this point of intersection here is 0. And then I need to figure out where the line y minus 2x intersects, because those are my bounds. So y minus 2x equal to, oh, sorry, I need to find the x-intercept. So I need to let y equal to 0. So y minus 2x, if I let y equal to 0, sorry, it's not y minus 2x, it's y equal 2 minus x. So if I let y equal to 0, then x is equal to 2. So my lower bound is 0, my upper bound is 2. So I'm going to collect area from 0 to 2. Now, something else that's interesting here that's going on is things change right there at that point of intersection between the red line and the blue line. Notice that from 0 to this yellow dotted line, the red line is on top. Y equal to x is on top, and the x-axis is on the bottom. The blue line is on top from this point where I have the yellow dotted line to 2. So the next thing that I have to figure out is where do the red and blue lines intersect? It's because I'm going to have 2 integrals here because the top and the bottom curve is changing. So let me create myself some space down here, get rid of all this stuff. Okay, so I'm going to set x, click the pen, x equal to the other line, 2 minus x, add x to both sides, 2x is equal to 2, and x is equal to 1. So right here at 1, the top curve changes. So instead of going from 0 to 2, I'm going to go from 0 to 1. Top curve is red, so the top curve is x, bottom curve is 0. Then I'm going to pick up the area again from 1 to 2 of the top curve. This time is the blue curve, so 2 minus x minus 0 dx. So I would have the integral, I'm going to go ahead and find the antiderivative. The antiderivative of x is x squared over 2, evaluated from 0 to 1, plus finding the antiderivative of the other function, 2x minus x squared over 2, evaluated from 1 to 2. And I would do this arithmetic and this arithmetic, fundamental theorem of calculus, add them together, and find the area that's enclosed between those 3 functions. Okay, number 25, and then we got 43, and then we're done. Number 25, I have f of x is equal to square root of 3x plus 1, and g of x is equal to x plus 1. The graph of this thing looks like we have a square root function. It's vertically shifted up 1 unit, and it's going to open to the right. The 3 is going to have an impact on the, like a horizontal shrink by a factor of 1/3. That's not really going to have an impact on how you do this problem. Also notice that the line y equal to x plus 1 is vertically shifted up 1 unit and would look something like that. So I have my graph, and I need to figure out where they intersect. So I'm going to set the square root of 3x plus 1 equal to x plus 1. The 1s are going to subtract out. So I'm going to move everything to one side. Well, actually, let's do this. I have the square root of 3x is equal to x. I'm going to square both sides to remove the radical, and I get 3x equal to x squared. Move everything to one side. 0 is equal to x squared minus 3x. Factor out the x, and I have x minus 3. So I have x equal to 0 and x equal to 3. So back up here on the graph, I know that the lower bound is 0 and the upper bound here is 3. And I can see that the blue curve, which in this case is the square root function, is on top and the line is on the bottom. So I'm going to collect area starting at 0, stopping at 3 of the top function, which is the square root of 3x plus 1, minus the bottom function, x plus 1 dx. I'm going to combine any like terms that I have here, so that would be 0 to 3 of the 1 minus 1 is going to subtract out, so I have the square root of 3x minus x dx. And that's the same thing as 0 to 3 of 3x to the 1/2 power minus x dx. Now, when you find the antiderivative of 3x to the 1/2 power, you might, it depends on where you are with this, but it's really a little u substitution problem. Some of you can do it without actually writing out the u substitution. U is equal to 3x, du is equal to 3 dx, and I divide by 3 and I divide by 3. And so I would have the integral 1/3, that's going to be the important part. I got to get 1/3 in there. The integral of u to the 1/2 power du, which is u to the 3/2 power times 2/3 times the 1/3, which gives me 2u to the 3/2 over 9. Okay? So when I resubstitute that back, blue, so that's going to give me 2. I'm going to replace the u. Remember, u was equal to 3x to the 3/2 power over 9 minus x squared over 2. That's just simple integration from 0 to 3. And then when you do the calculations, I'm going to walk you through this just to get a little bit of algebra practice in here. Let me make myself a little room here. Come on. All right, the eraser is very small. Let's make the eraser bigger. Okay, so make some room here. Sorry about that. So I'll have 2 times 3 times 3 to the 3/2 power over 9 minus 3 squared is 9, so I have 9/2 minus 0. That's good. That's easy. Now 3 times 3 on the inside here is 9. The square root of 9 is 3. 3 cubed is 27. 27 divided by 9 is 3. Times 2 is 6. Minus 9/2. Now let me walk through that again. On the inside, 3 times 3 is 9. The square root of 9 is 3. 3 cubed is 27. 27 divided by 9 is 3. 3 times 2 is 6. So that's the same thing as 12/2 minus 9/2, which is 3/2. Now hopefully I didn't make any mistake in there. I was going pretty fast. If so, please feel free to call me on it, and I'll make a correction. All right, let's get to the last problem. Last problem, I believe, is number 43. Let me verify that. Yep, number 43. Oh, it's a trig one. So 43 is f of x is equal to 2 sine of x, and g of x is equal to tangent x, and they're already telling us that we're bound from negative pi over 3 to pi over 3. All right, first of all, let's get a graph going over here. Remember, you know what a basic sine wave looks like, and so this is multiplied by 2, so the amplitude, instead of being 1, is going to be 2. Everything else about the graph is going to be the same. I'm going to graph this to 2 pi. It's pi over 2, 3 pi over 2. So we're going to hit our peak at pi over 2, intercept, minimum. All right, so there's a rough graph of 2 sine x. Now, remember, tangent x has intercepts at negative pi over 2, at pi over 2, and 3 pi over 2. Because remember, tangent is sine over cosine, And wherever the cosine is 0, we're going to have vertical asymptotes. Cosine, the x value is 0 at pi over 2 and 3 pi over 2. In the first quadrant, the tangent is positive, and in the second quadrant, the tangent is negative. But this one was going from negative pi over 3 to pi over 3, so here's going to be negative pi over 2. So pi over 3 is approximately here, and negative pi over 3 is about here, and pi over 3 is about here. So we need to continue the sine wave, which goes like that. So the only thing that's going to go on here is that there's negative pi over 3, there's positive pi over 3. The big deal is that in the on the left side of the x-axis, right here, the tangent curve is on top, and on the other side, the sine curve is on top. So basically, what you have going on here is you're going to collect the area starting at negative pi over 3 to 0, which is where everything changes. The tangent curve is on top first, minus the sine curve dx. And then we're going to add that to the area that we collect from 0 to positive pi over 3. The sine curve is on top, minus the tangent curve is on bottom. Now we're going to find the antiderivative of tangent. We're going to find the antiderivative of sine. The antiderivative of tangent is negative ln of the absolute value of cosine of x minus the antiderivative of sine is negative cosine. And then we're going to do the same thing, except that's going to be from negative pi over 3. You know what else I noticed? Those areas are equal. Let's not go through all this trouble. Look at the graph. Answers are 0. They're symmetrical. Okay, so hopefully you found this video helpful. If not, please come and see me. If you found any errors, please feel free to share those with me, because I did these on the fly and I tried to do it quickly, but I wanted you to have some access to how to work these problems. So I hope this is helpful.